For this video, let us try to determine the subgroups of a given set G containing the elements 1, 2, 3, and 4 under multiplication modulo 5. In one of the videos in this playlist, we're able to determine that this set G is already a group, and this time we are to determine the subgroups of this given group. Subgroups, as guided, is that they are also subsets of the given group, which also exhibits the axioms of a group. So in this case, we are to determine, based on this given KD table, we will be using that later on, about the subgroups of this given set. Now, before we start, let us try to introduce or reintroduce the Lagrange theorem, because this will tell us a little bit of guide on determining what will be our subgroup. The Lagrange theorem tells us that the order of G is actually, again, the cardinality of set G, meaning there are 4 elements, okay? And that means that the order of any subgroup H of your group G would be the factors or positive divisors of your order of your group G. In this case, it's 4, so the positive divisors of 4 are actually 1, 2, and 4. This guide will tell us about the possibility of coming up with subgroups of this order 1, 2, and 4. The other thing for this is a guide that we will no longer try to identify any possibility for a subgroup with order 3, because according to Lagrange theorem, 3 or any subgroup of order 3 is not possible. So let's start now writing the subgroups of this given group. Now, the first subgroup you must not forget is always the set itself containing 1, 2, 3, and 4. This is what we consider as the improper subgroup, because as mentioned, the set itself is also a subset, and since the set itself is already a group, therefore this subset is also a group, the group itself. Okay, this also embodies the subgroup with order 4. So hence we will no longer, since there are only 4 elements, we will no longer come up with any other combinations of 4 elements, because we're talking about the set. That is already okay for our order of subgroup of order 4. Now let's talk about the subgroup of order 1. That's actually our second subgroup. It's the subgroup or a set containing the identity of our group G. Take note that for an identity of group G, and since subgroups are subsets, they must have the same identity of our set G. So looking into our subgroup diagram, we would be able to identify our identity to this. You may want to review the video discussing the proof for the given set to be a group, because it's already there as well. But for the purpose of the discussion, let us talk about that. I would like to introduce you to a certain column or row where the used elements do not change their respective value. That's your guide that your identity can be found in that specific portion. Looking into this, we know that the identity is a certain element that when multiplied, or in this case operated using the binary operation multiplication modulo 5, will not change any of the elements that will be used. In this case, we have here 1 star 1, the result is 1. 2 star 1 is 2, 3 star 1 is 3, 4 star 1 is 4. So when we try to operate all of these elements by 1, so the values will be retained. Similarly, we have 1 star 1 is 1, 1 star 2 is 2, 1 star 3 is 3, 1 star 4 is 4. 1 is also when operated with any of the elements, those elements will not be changed. Therefore, in this case, our identity element is equal to 1. So if we're talking about the subgroup of order 1, it's actually just a subgroup containing your identity element 1. So again, that's for the subgroup of order 1. Now here comes the next part as we try to identify subgroup of order 2. Okay? Subgroup of order 2. That would mean we are going to pick pairs of elements here and verify later on if they actually exhibit the axioms of a group. So we're talking about pairs of elements. Okay, we are going to use the pairs of elements containing 1, because the next consideration in identification of a subgroup is that since it's a group in its sense, there should be the existence of the identity element. And since our identity element is 1, so 1 should always be one of those elements in our pairs. So you have here 1 and we don't know. You also have 1 and another thing. And you have here 1 and another element. Since there are only 3 other elements aside from 1 for this given set, you have 2, 3, 4. So you have 1 and 2, 1 and 3, 1 and 4. These are not yet subgroups, but we are to verify them. Since they all satisfy with the existence of identity element, let's proceed to the existence of the inverses. The inverse means that if we have 1, the inverse of 1 should be there. If we have 2, the inverse of 2 should be there as well. Okay? Now, take note that we will not be writing here 1 and 1 because, that pair is already written as the singleton because we don't need to write duplicates when we talk about the set. So let's start with 1 and 2. But first, since we're talking about inverse elements, let's go back to our KD table and determine the corresponding inverses for our every element. So we need to show as well the inverses so that we will be guided later on our next step. The inverses is actually a similar element in a given set that when operated to a certain element, they will result to the identity. Hence here, I would like you to focus on the identity element 1 on our KD table. And what are the elements that are actually operated that would result to that? Looking into the first, we will only get 1. Sorry for that. Let me resize this one. Okay. So for this, when we get 1, it is actually when 1 is operated by 1. In short, the inverse of 1 is 1. Second row, when do we get 1 here? It's when we operate 2 by 3. Therefore, the inverse of 2 is 3. Next, for 3, it's here. So it's the result when we operate 3 and 2. So the inverse of 3 is 2. And finally, for our 4, it's here. It's the result when we have 4 star 4. So the inverse of 4 is 4. Now, these are the considerations that should also exist on our pair. So, talking about the subgroup of order 2, for it to be considered a subgroup. Because we already are assured with the existence of identity, let's proceed to the existence of the inverse elements. Now here, if we're talking about 1, the inverse of 1 is actually 1. So it's okay. But the inverse of 2 is 3. And since 3 is not here, we automatically drop that. Of course, you can always add the 3 there, but since we are talking about order 2, it's already 3, so no longer doing that, it's already dropped. Similarly, for our second, the inverse of 1 is 1, but the inverse of 3 is 2, so drop that as well. Now, for the third pair, you have the inverse of 1 is 1, and the inverse of 4 is 4. So this is already okay. Might be considered. I'm not saying it's already subgroup, but this is already considering the first two considerations, the existence of identity and inverse elements, because we still need to check whether it's actually closed under your star. Meaning, if we're going to operate 1 by 4 and 4 by 1, even 4 by 4 and 1 by 4, all the results here must be either 1 or 4. If some results will give 2 or 3, then we drop this as well. Going in our KD table, take that we're operating 1 and 4. So we have 1 star 4 is 4. Check, because 4 is one of the elements. Next, for 4 and 1, so it's still 4, it's okay. 1 by 1 is actually 1, and 4 star 4 is equal to 1. So we have here again 1 star 4 is actually 4, 4 star 1 is 4, 4 star 4 is 1, the other one should be 1 star 1, okay, is actually 1. So these 4 elements are also elements of this. Therefore, we check that. It satisfies the existence of identity, it satisfies the existence of all inverse elements, and it is closed under star. So this is our subgroup with order 2. Now, this is now the end of this video, since we will no longer try solving for order 3 because according to the language theorem, it's no longer possible. Hence, we have here our subgroups for group G containing 1, 2, 3, and 4. The subgroups are as follows. The G itself, 1, 2, 3, 4. The set containing the identity, which is set containing 1. And then this one here containing 1 and 4. So we only have 3 different subgroups for this given group. Thank you very much for watching.